Okay, so let's get started with Reynold stress modeling. So far we have been seeing only this eddy viscosity modeling, right? So we'll go to the next level of uh, complexity. So which is Reynold stress modeling, RSM. Sometimes it's also called Reynold stress transport modeling because you are solving a transport equation for each of the Reynold stresses. So Reynolds stress transport modeling. RSTM. These are also called as second moment closures because in the when we did eddy viscosity modeling, we primarily closed the momentum equation, right? Your u bar, v bar, w bar equations were closed by modeling the Reynold stresses using Boussinesq. So that is the first moment closure. So this particular class of models, that is Reynold stress models, RSMs, are called second moment closures. The name comes because here we are solving for um, uh, Reynold stresses itself. That means we are solving the closed form of Reynold stress equations, the second moments. That is we are solving closed form of your Reynold stress equations. The transport equations are being solved here. So if you recall now from eddy viscosity models, you had 6 unknowns in the Rance equation, right? So if you recall Rance equation, you have 6 unknowns, that is your ui prime, uj prime, average, 6 stresses, 3 normal stresses, 3 shear stresses, and in the eddy viscosity model this was closed using Boussinesq. Here we are not doing anything of that sort, okay? So in RSM, okay, no Boussinesq is used. Used to close the unknowns. So instead we solve for a transport equation for each of the stresses, okay? So instead we solve the transport equation for each Reynold stresses. But it requires modeling because this equation, you saw that it has far too many unknowns, right? The Reynold stress equation that we derived from first principles, if you recollect, right? So the exact form of equation, so the exact equation looks like dou by dou t of your ui prime uj prime plus uk bar dou ui prime uj prime by dou xk. In some literature, and I think if I recollect correctly, even when we derived, j was the repeated index and it was I prime k prime. You can throughout replace the divergence term here, the index k, with the j. So in some literature it is interchanged. So you will get ui prime uk prime and divergence term will be dou xj, okay? Yes, but we will take up this because in the when we model the turbulence kinetic energy equation and the eddy viscosity, we use ui prime uj prime average. So for consistency, I am taking that and making k as the repeated index, the divergence term. That's it. Okay. When you expand it, it doesn't change, right? We have throughout replaced I with j. Sorry, k. Yeah, j and k are interchanged throughout. So on the right hand side is the trouble. You have extra unknowns. First, we have the the diffusion rate term, which is dou by dou xj of dou by dou xk, sorry, dou by dou xk of, I have the minus p prime uj prime by rho delta ik, and then minus p prime ui prime by rho delta jk. Okay, so this was your pressure diffusion rate, and then I have the turbulent diffusion rate, which is minus ui prime uj prime uk prime, the 27 unknowns, and then the viscous diffusion rate, which is nu dou by dou xk of your ui prime uj prime average. So this is your diffusion rate. Symbolically, let's say I write it as dij. This can also be symbolically written as cij here, the advection rate or the convection rate term, cij dij term. And then I have the pressure strain rate term. This we escaped in the turbulence kinetic energy equation by continuity, but that term appears here, which is good because this will take care of your redistribution rate, and therefore it takes care of anisotropic nature of turbulence. It also handles your two component limit. So there is a lot of advantage of this term coming back to the equation, not for modeling, not from the modeling perspective, because pressure term we always ignored, but this term we cannot. So this is an important term in the Reynold stress equation. So we have this p prime by rho, and then the strain rate fluctuations, which is dou ui prime by dou xj plus dou uj prime by dou xi. The pressure strain rate. What did we use the symbol here? Is it phi ij or, okay, you can use this, or sometimes this is also used in the literature symbolically. So I have the two terms and then two more, which is the production rate term. So I have minus ui prime uk prime average dou uj bar by dou xk minus uj prime uk prime dou ui bar by dou xk. So this is your production rate, you can call it Pij, and finally the dissipation rate term, which is minus 2 nu dou ui prime by dou xk dou uj prime by dou xk. This is your dissipation rate term. We call it epsilon ij, let's say, symbolically. So we have the exact equation available. We just need to go ahead and model the equations now. Of course, it has more unknowns than the k equations, but we will see what we can do with that. So the left hand side need not be modeled. nothing to model on the left hand side. So I have access to the Reynold stresses here, right? So nothing to model on LHS. Only on the right hand side I have the terms that are unknown. We can take up with the diffusion rate term first, Dij term. So Dij model. Okay. So before that I would like to talk about interesting advantage here. We'll take up the production rate, Pij. So now the question is, do we need to model this? The production rate of turbulence kinetic energy, Pk, was modeled, right? It had Reynold stresses working against the mean strain rate terms, right? Minus ui prime uj prime over bar with dou ui bar by dou xj. That term was there. So that was modeled using Boussinesq. What about here? The production rate term? Sorry? Yeah, we don't have to model this at all because you are computing for the Reynold stresses, so it's available to you. You have access to Reynold stresses here, right? So this is the biggest advantage of RSM, no production rate to be modeled. Okay, so this is the best part of the RSM here, right? Because Reynold stresses are available to you. That's because Reynold stresses your ui prime uk prime average is being computed and therefore available. Therefore, it's readily available. Okay, so no Boussinesq assumptions here. Required here. Which is a good part. The production rates are not modeled. Okay, so the Pij is not modeled in RSM, biggest advantage. This is the biggest advantage in terms of RSM, since Pij is not modeled. So Pij is already readily taken care of. I don't have to do anything with it. That means I have only diffusion, pressure strain rate and dissipation rates to be modeled. But you have to, since you have already been looking into a viscosity model and its solutions, you can see that the coupling is very intense here now for the production rate term Pij. Okay, so earlier you had in the viscosity model you have the Rance equation where it is coupled to the, you need to compute Reynold stresses, you need the eddy viscosity, and eddy viscosity required k epsilon or k omega and so on. So you are solving for essentially velocity equations which requires eddy viscosity, which requires k or epsilon and so on, and they also require velocities. So it is all coupled. This is much more coupled than that one, right? So you can easily see. So however, strong coupling okay, so you need to be aware of this. So you need to have some CFD techniques to make sure that the model converges. So we can see this, what kind of coupling that we are talking about. So if I have, let's say I take up example, say I equal to j equal to 1. You are computing the one of the normal stresses, which is u, that means I am looking into the P11 term here, Pij I equal to j equal to 1, P11 term is essentially minus 2, okay, minus 2 of, because I and j equal to 1, so minus 2 of ui prime, not ui, sorry, u1 prime, uk prime, and then dou u1 bar by dou xk, I equal to j equal to 1. So this gives me sum of 3 terms to compute production rate for 1 for one of the Reynold stresses. That is, this is the equation is u1 prime equation. P11 appears in u1 prime transport equation. For that, now I get minus 2 u1 prime average dou u1 bar by dou x1 minus 2 u1 prime u2 prime dou u1 bar by dou x2 minus 2 u1 prime u3 prime dou u1 bar by dou x3. So that means to compute for this particular stress here, u1 prime average, you would need access to u1 prime itself and the two shear stress terms, u1 prime u2 prime and u1 prime u3 prime average. So this equation is coupled to itself as well as the two extra equations, the transport equation for u1 prime u2 prime average and transport equation for u1 prime u3 prime average. So we can see what does u1 prime u2 prime depend on. Okay, so this here we can say u1 prime equation is coupled to u1 prime u2 prime and u1 prime u3 prime equation. So what does this I equal to 1 and then I said j equal to 2. So I get the u1 prime u2 prime equation. So I get P12, the production rate for the one shear stress term, that will be minus u1 prime uk prime dou u2 bar by dou xk minus u2 prime uk prime dou u1 bar by dou xk. I is 1, j is 2. So if I expand this, you will see what is the coupling that will happen here. So I get minus u1 prime dou u2 bar by dou x1 minus u1 prime u2 prime dou u2 bar by dou x2 minus u1 prime u3 prime dou u2 bar by dou x3, and then the next term, which is u2 prime u1 prime dou u1 bar by dou x1 minus u2 prime dou u1 bar by dou x2 minus u2 prime u3 prime dou u1 bar by dou x3. So the production rate for u1 prime u2 prime bar shear stress depends on 6 stress terms, which is u1 prime. So to compute u1 prime average, you needed u1 prime u2 prime average, and to compute u1 prime u2 prime average, you would need u1 prime average. They are strongly coupled to each other. In addition to that, they are of course also coupled to the other stress terms and other normal stress terms also, right. So u1 prime u2 prime equation is strongly, or can just say coupled to u1 prime u1 prime, u1 prime u2 prime, u1 prime u3 prime, and then u2 prime u2 prime and u2 prime u3 prime. 5 components. That's why I mentioned strong coupling. Strong coupled system of equations. So make generous use of under relaxation here to get any converged solution. Okay. Generous use of under relaxation is recommended in CFD calculations. To get convergence. Advantage is good, no need to model production rate, but a strongly coupled system of equations. You are solving 6 extra transport equations here, which is closely linked to each other, and with the momentum equations, 3 momentum equations, which is also of course linked to the pressure equation. Okay, so production rate is sorted. So now I have the diffusion rate term.